What you just heard can be explained using maths. A sinusoidal function is a function whose graph oscillates infinitely and can be expressed as a sine function. Music is made up of sound waves, and these sound waves are sinusoidal functions. Let's watch the tune again, and this time look at the sound waves that are created by the music. The graph of the sound waves becomes taller every time a chord is played. What happened was that basically the sound waves went from this to this. The graph experiences an increase in amplitude. Amplitude is the absolute value of A in the equation of a sine graph, and graphically it is half the height of the wave. So if you increase the value of A, the wave gets taller. This is called a vertical stretch. If you decrease the value of A, the wave gets shorter. This is called a vertical shrink. And when talking about music, amplitude represents volume. The louder the music is, the greater the amplitude, and the taller the sound waves. Sinusoids oscillate infinitely, and so the period is the length it takes the graph to complete one full cycle. It is equal to 2 pi over b, b being the coefficient of x in the basic equation of a sine graph. Frequency is the reciprocal of the period, so frequency and period are inversely proportional. High frequencies result in shorter periods. This explains the equation for the graph of a sound wave. You start with the basic equation of sine, and since you know what frequency is, you can rearrange the formula to find b. Substitute b for frequency multiplied by 2 pi, and rearrange the equation, and you get the equation for a sound wave. Frequency is also pitch. The higher the frequency, the higher the sound, and the shorter the period. Just take a look at the repeating melody and its score. The notes get higher from E to F to C. And as you can see, the frequencies get higher, making the periods shorter. Frequency also explains why music, and sound in general, becomes a lower pitch when it is slowed down. Since the x-axis is time, just increasing the time frame is the same as stretching the music horizontally. This increases the period, meaning that the frequency has decreased and the music is now a lower pitch. The more intersecting zeros that the sine graphs of two notes have, the better they sound together, or in other words, the more consonant they are. For instance, if every zero intersects, the two notes are exactly the same. If every second zero intersects, the two notes are the same but separated by 1 octave. If every third zero intersects, the notes create a chord. Let's see the latter two examples in action. These are the chords that were played. Take a look at the bass notes that were played. They are the same notes used in the chords, but in a lower octave. These are the graphs for B flat. One is the B flat played by the bass, and the other is the B flat that is part of the chords. And you can see how they intersect at the higher notes every second zero. Now take a look at how the first and fifth notes of these scales intersect. These are the graphs for B flat and F, which make up the B flat major, and you can see how they intersect at the higher notes every third zero. But why do these rules work? Well, it is because of this. The ratio between each note in the Western scale is exactly the same, and this is why the same music theory rules apply for all octaves and all notes, like the formation of triads, which is the first, third, and fifth notes of a scale played together. We can see this ratio clearly by how the ratio between octaves is always 1 to 2. Intersection is how we see consonants graphically, but in general, The simpler the ratio between notes, the more consonant they are. Chords are several notes played together, and when two or more notes are played at the same time, the individual notes have to be added together to create the resulting sound wave. Let's see what the sound wave of the first and fifth notes of B flat major played together looks like. Now this is where music gets to explain maths, and not the other way around. A mathematical rule is that only when A equals B is the sum of the two sine graphs also a sinusoid. The blue wave is note 1, the purple wave is note 2, and the green line is the resulting sound. From music, we know that the two sound waves with the same B value have the same frequency and are therefore the same note. When the same two notes are played, you get the same note, but louder. And all simple single-note sound waves are sine graphs. A musical experience isn't complete without noise-canceling headphones. What if I told you that the silence you hear when you use them is actually added sound? It is based on the mathematical principle that the sum of a sine graph and the same sine graph with a phase shift of half a period is a sine graph of amplitude 0. If this is the original sine graph, then this is what it becomes after a horizontal shift of half its period, which is the same as it being reflected across the x-axis. So when the two sounds are played together, we are left with 0. Surrounding noise is nullified by more noise.